Okay, well, welcome to our problem session. We're just working out the mechanics of this so that everything gets duly recorded so people will know which conjecture they've solved, and when they publish it in the annals, they can appropriately cite it. Right, so.
Will there be some sort of file made afterwards of the problems?
I'm about to tell you. Okay, so Ilias is actually going to chair the session, choose who can speak, who can't, cut people off very rigorously. I will write on the board whatever people want me to write, and Jen over here will record it in a beautiful format, which we will then circulate. Okay, is that good with everybody? All right, so I have to wear this mic apparently so that the camera follows me, so it watches what I write on the board, but I hopefully won't have to say anything. So now it's Ilias's turn.
Any questions?
Yes. So, I forgot to say, so we have a quick limit on one turn, so you can have another. I mean, if we have like 9 minutes worth of questions, you can have 3 turns after people.
Oh, okay. So I cannot speak continuously for more than 3 minutes.
Yes, that's correct.
Okay, so I just state my open question, or?
Yep.
Okay. Right, so if n is a 2-1 factor, such that it is existentially closed in M, which is also a 2-1 factor, then M has property T implies N has property T. Yeah, this is the question. Yeah, it's my conjecture. And the reason I make this conjecture is because in the group case, if you look at group ultra power, this is true by a theorem of Shalom, which I leave to you as exercise. I don't think it's written anywhere, but it's like pretty easy consequence of theorem of Shalom, which states that any property T group is a quotient of a finitely presented property T group. Unfortunately, in von Neumann algebra theory, this Shalom's theorem analog does not exist because it goes through reduced cohomology. By the way, I should give some credit to Jesse Peterson for this question because it came up in conversation with him, but he didn't phrase it like this. I am the one who phrased it like this.
Okay.
Yeah.
Shree's fault. Right. Okay.
Right. So non-amenable. N is a non-amenable one.
That's a carrot on this. What was the end of this sentence? The motivating thing was that if you have a property T group, then it's a quotient of.
Yeah, finitely presented property.
So I can't. If there's a.
Please isolate the point.
It's property bracket T bracket.
Okay.
Okay, so is my 3 minutes up or?
Yep.
Okay.
Yes.
Any other questions? Okay, so yes, go.
Yeah, so know that there's assuming diamond, there are examples of inductive limits of length L1 of copies of the car algebra, which are not isomorphic to their opposites, and same goes for a hyperfinite 2-1 factor. So that's no. Okay. And the question is this independent of ZFC? And there's a question two, same question with the hyperfine into one factor in the phenomenon first one. Yeah, the theorem is with, yeah. The question is, we need diamond.
So, so this is true in the von Neumann algebra case as well?
Same thing, yeah.
Same proof,
Same thing
same
is true
proof.
for,
Yeah.
Same proof, the same thing. And this question about diamond is, can we use diamond or some other axiom to construct one of those things, inductive limits of the car algebra or the hyperplanar to one factor, which are isomorphic to their opposites, but not via an order 2 anti-isomorphism. So the significance there is that this means that they're isomorphic to their opposites, but they're not complexifications of a real Caesar algebra or something like that.
Not via,
An order 2.
oh, our scribe will record who said it.
Any other, of course, you can also comment on questions, but actually I already did. Any please.
So these are things which may in fact already be known, in which case I'd like to know. So I'll start with this. Among, let's say, Banach algebras, and the category should be contractive morphisms, are C-star algebras axiomatizable? So this would be a Banach algebra is isometrically isomorphic to a C-star algebra.
You mean without the
Yes, that's right. Yeah, I want to axiomatize without mentioning adjoints.
So for the model theorists in the crowd, the language would be the language of
Language of Banach
Banach algebras.
but no mention of adjoint.
No, and nothing else. No. Okay.
I suppose I'm not an expert in this, but that's
Yeah, you might want to have other symbols that.
we have to have the norm.
Yeah. So you've got the norm, but. Right, not adjoint, right, but this might be true if you had some sort of trace of the adjoint somehow that was there, or you really care just as Banach algebra.
Just as Banach algebras, yes.
All right,
I mean, I
okay.
have some motivation for this question, which I will go into, but so I mean, my understanding is that what you would want is its classes close under isomorphism, close under ultrapowers, and close under what was it, ultra roots.
Ultra roots, yeah.
And I don't know. I thought about that briefly, but I don't know whether this is close under ultra roots or not. There's some other. If it is axiomatizable, I'd like to actually know some axioms. Well, how do you know the subalgebra in the Banach situation has the same adjoint? Or even hasn't, or that it's closer to the adjoint?
Yes, yeah, it'd be the closure of the subalgebra under adjoint would be the issue.
Right, you take a,
I mean, it's ultra roots, you don't care about the subalgebra.
yes.
Well, no, but
does
you
that-
care about the diagonal
Yeah,
subalgebra. would-
okay, sure, but I don't know whether it helps or not. Maybe it does, maybe it's obvious.
No, all you know in the general case is that the ultra power is isomorphic to a C-star algebra. So you've got some adjoint, but it doesn't tell you that the diagonal embedding is invariant under that adjoint.
And okay, so given what I've seen, one can ask, okay, is it axiomatizable? Is it effectively axiomatizable? You actually find some axioms which I can use.
Sadly, the answer is usually to the latter half of that. It's usually no, but. Okay.
Yeah, so I've got two more things of the same general nature.
Okay, we'll go around the room and we'll come back to you.
Can I say something about that? So it's a result of Palmer that a Banach algebra is a C-star algebra if and only if it's spanned by its Hermitian elements. And being Hermitian, that's a Banach algebra property. And then the Hermitian elements are exactly the self-adjoint elements.
I need a proof 4, so you can show now. Oh, but it's not here.
Hermitian means so that e to the ita is not 1 all real numbers. So that's encoded in the form.
Oh, so that would descend to the diagonal subalgebra.
Yes.
Okay, so then the answer is apparently true. It's apparently solved. Yeah.
Okay, but the other two may not.
You're right. Okay.
That's what I want to know. This is something
Okay.
I just wanted to mention a remark about the first question. It's just 10 seconds.
It's your question.
Yeah, about my question.
So the David goes first.
Okay, so the remark I wanted to make was that if this holds, then you can find in my paper that n is not isomorphic to the free group factor. So that's some evidence for this.
Okay, so this is a question which probably have thought about before if you worked on model theory of operator algebras, which is you have a matrix ultraproduct with two different ultrafilters. Are they elementarily equivalent to each other? And you could in fact ask this. I mean, I've only thought about the von Neumann algebra version, but there's a C-star algebra version as well. I don't know if people know that already, but yeah, this is an important question.
This is cheaper version, it has even more multiplication.
Okay. And anyway, and a possible idea to do this, right, to perhaps try to think about, just their two quantifier theory, are they the same, is you could have some kind of statement like the following, like say you have a certain group with some magical property that, and you write a sentence that asks, like, for any approximate representation of the group, is there some non-trivial projection that commutes with it, right, which is kind of testing if all the if all the representations in that dimension are reducible, but in an approximate version. And if you could magically find some group where you could have approximate representations that were very irreducible in some dimensions, and in some dimensions you could not, then this would allow you to distinguish the two quantifiers. But since I do not know enough of representation theory, I do not know like how you could construct such a group, right? And it seems like it's kind of a challenge.
Should I write the comment down as well as the question, or I mean, yeah. So I think can you construct a group
Yeah, so
G
you want to construct a group G,
with irreducible representations on Cn for some n, for some n's, and not on others.
Yeah, this already exists.
but I mean, this has to be like approximate representations have to be.
Right.
You have to ask whether the approximate representations are approximately reducible, so that you can make this.
Is that a sufficient version of it, or would you write something else?
I guess this is good enough, right? Because it's not just good enough to say, oh, I have exact representations in certain dimensions, right? You have to control approximate representations, which is why it's harder.
Right. I mean,
and I guess another question might be, say you take two different ultrafilters, like maybe two specific ones, then is it decidable or computable, like whether the matrix ultraproducts are isomorphic or not? Like maybe there's some kind of
there's too many ultrafilters. that one.
Well, just fix it. Yeah, maybe
Just two given to you somehow. It's very hard to get unless they're not elementarily equivalent. Right. Yeah, if CH holds, they're isomorphic unless they're not elementarily equivalent. So
yeah, so I'm saying something like maybe pick two subsets of the integers, for instance, right, and then try to ask if you can compute the limit of the theories in the one subset or in the other subset of integers.
or for a given fixed subset of the integers.
Yeah. I'm just saying, like, maybe there's some kind of decidability thing to either prove that it can't be isomorphic or to prove that it's a difficult problem.
The fact that it's been open for 12 years indicates it's difficult.
Well, let's hope it's difficult.
Yeah, if it turns out to be.
Okay, so more questions, but please just restrict to questions in the first one, and then we can discuss questions. So if there is nobody, then there is Peter.
So yeah, related to some of the elementary equivalence things that we have seen before, a problem, can you find two Neumann algebras with property gamma, but that are not McDuff, that are not elementary equivalent? So we
Sorry.
know, so find two one factors with property gamma, but without property McDuff, that are not elementary equivalent. As far as I know, this is open. We have a lot of examples that are McDuff.
Okay, so with property
gamma, not
but
McDuff.
not McDuff. Right. Good. Yeah, we know the answer to this, but I'll write it down anyway. Yes, there are continuum many.
And what are they?
You missed something that are not elementarily equivalent.
Not McDuff, which are right. So there's not continuum many. My student Stephen Lazaro proved this. So Stephen Lazaro. I always get it wrong. 2 Zs, 1 R.
2 Zs, 1 R. Yeah.
That's right.
Okay. Sorry, I don't mind.
Okay. Yeah.
Okay, great. So what are they?
It's
Allowed to give away
Okay, but that was a question.
yeah. You can give away secrets. Okay. Yes, Stephen can tell you about them.
All right.
Well, I could ask a number of questions about what happens without the axiom of choice, but one question I've been wondering about that I didn't really talk about is how much of the theory of AF algebras works without countable choice, and what's really the what do you need to put into the definition of an AF algebra? Without countable choice, AF algebra is not completely determined by either Bradley diagram or its dimension group. But if you require that an AF algebra be separable, it might be enough. So I guess the question is, if you include a requirement of separability in the definition of an AF algebra, does a Bradley diagram or dimension group uniquely determine the AF algebra?
The Bradley diagram and the dimension group are equivalent.
Are they without choice? Are they without choice?
Yeah, wait, well, okay.
The answer should be you don't know because nobody knows what goes on without choice.
Yeah, I think it's probably the same question.
Right. So yeah. Okay. So we'll just leave it at that. The real question is whether the K theory and the Bradley diagram are
In this, if you require that they be separable. Yeah.
right. Where does choice come up, like most obviously in this question?
Intertwining, you have to choose a whole lot of inner isomorphism. We have the intertwining at the K0 level, but then you can lift individual K0 maps to finite dimensional algebras.
I see. So you have to.
You have to then make it commutative. You have to use uniqueness.
Right. I see. And you're just making constant series of choices. Yeah. Yeah.
You get a limit, maybe you can sort of intertwine at every stage, but you can't do a global intertwining.
I couldn't actually hear the last bit because there was a brief musical interlude, but okay. But okay, I think I got the point.
Small time to journey. So, okay. So, any other questions? Actually, I had a.
Oh, no, hold it. Didn't you already? Because we should go through everybody unique and then. This is the theme music of the problem session. Okay, Ilias.
So actually, I had a right. So this is if I know what we're talking about. This is the question that then was asked the first time we talked 15 years ago. But I knew so little that I'm not sure that was the question that was asked. So can one develop this integration theory for, let's say, creation of Neumann algebras, which not necessarily have separable review. So this is more of a problem than a question. But there are several questions related to that. So Andrea and I worked a lot on ultra powers. But I'm going to state actually I guess a question that is relatively famous. Taka Ozawa asked it on Math Overflow a couple of years ago. He called it exercise. And so exercise is if you have factors m and n, he just said factors, but let's say 2, 1 factors. And you know that L infinity of 0, 1 tensor m is isomorphic to L infinity 0, 1 tensor n. Can you conclude that m and n are isomorphic?
Hold on, what was the isomorphism?
L infinity 0, 1. Big L infinity. No, for a little one, I can do it, yes. So everybody can do it. But this is anything far on top of this. It's fundamental.
You probably write your ultraproducts with some superscripts and subscripts, right? Then M is isomorphic then.
Right. So of course, if M and N have several residuals, the answer is yes. But actually, if additivity of measure is greater than density characters of M and N, the answer is again yes. But the question is really, can you have
So the exercise is for separable, or the exercise is
for separable? It's a theory.
no, right? So it makes it an exercise, but
Yes.
you're saying
Taka called it exercise. I think it's not sound like exercise, but exercise that is unsolved. So it's,
okay. So this is an open problem exercise.
Russian unsolvable exercises.
That's right. What's the point of asking something that the answer is no? Yeah.
I think there's not known
Right. So open for.
It's bigger than additivity to a measure. But actually, there is David Guo. I think he has a paper in the archive. He proved that M and N do have same density character, and they are elemental equivalent, and that they're very similar. And actually, forcing with a big measure algebra makes them isomorphic. So this actually becomes sort of not a theoretic question.
Okay. What's the open question? What's the?
That's it. Just is it consistent with the FC?
Oh, I see. Is this true? Exercise. Is this true? Is this true in ZFC?
So for set theories, a remark, if there are non-isomorphic M and N, such that this happens, actually this isomorphism is equivalent to adding a random real, making M and N isomorphic. So isomorphism is really the name in the forcing notion by random real.
So if you add a random real and M and N become isomorphic, yes. Were they isomorphic to begin with?
Exactly. That's a sort of a logician's way of asking the question.
Right.
Okay, so who can need question? So it's a new question.
Hold it.
Yeah.
Don't I get a question? Don't I get a question? Well, hold it, but I can talk, so I can. Okay. This is a question with Isaac Goldberg, which we thought he should ask at the end of his talk the other day, but he decided not to. Okay, so we have the following classes of C-star algebras. We have all C-star algebras, right? We have nuclear C-star algebras. We have ones that have WEP. We have ones that have QWEP. And then we have this strange class that we said have the Cyrildson property from Isaac's talk, okay? This class is an elementary class. This class is not. So we're just going to think of the theory of these things. We think about the theory of these because WEP is not an elementary class, but by the results of Isaac, QWEP is. And by what we proved in our paper, the Cyrildson property is also gives you a class of, an elementary class of C-star algebras. In the model theory of C-star algebra book, we showed that the class of models here are not the same. There are C-star algebras which are not models of the theory of nuclear algebras. And by MIP star equals RE, there are C-star algebras which are not QWEP. What are the containments between all the other classes, right? So we know that this isn't that, and this isn't that, and we actually know a concrete example of that. What about all these inclusions here? Which ones are proper? We asked Ozawa whether these two classes are different. A lot of the properties of Cyrildson, things that have the Cyrildson property, are the same properties that QWEP has. But we couldn't prove these two classes are the same. They might be different, I don't know. But, and then, I mean, given that to separate this and this, we need MIP star equals RE, separating these classes might be a little hard. Okay, but yeah, so that's the question. Yeah, and just notice, right, that things get, this has a recursive axiomatization. This doesn't, this doesn't, this doesn't, this doesn't. These are all bad from a axiomatic point of view. Okay, anyway, there's many open questions there. Bruce?
It's a stupid question, but where do we exact C-star algebras fit into this?
Right. Every exact thing WEP?
We don't know whether there is anything that is not a model of an exact C structure.
Right, right. So we get, yeah, you could put the theory of exact things in here, and we don't know, like that might actually be equal to the models of this. It might be equal to the models of that. We don't know.
No, it's not equal to most nuclear because we have exact C structures which are not.
Oh, is that what our,
Well,
are the
because
type
of
three,
the-
the type 3
The
VNA?
McDuff thing, just
Yeah.
reduced group algebra.
Okay, okay. We know these are not equal, right? But it could very well be that the theory of exact things is probably not true, but we don't know a counterexample that the theory of exact C-star algebras could be everything. Okay.
Yeah, so yeah, there's nothing wrong with my question, but I wanted to add maybe something to Peter's question that would make it a question and not a theorem. Is that can you find M and N con-embeddable?
All of those examples are con-embeddable.
They're all con-embeddable?
Yeah,
Okay,
yeah.
that's fantastic.
Yeah,
Then-
yeah, okay.
Okay.
Right,
so-
that's true, right, Stephen? And they're all con-embeddable. It's a concrete, the short version is it's the BC, no, it's the McDuff. Yeah, use the group set. Yeah, and then you do have to then check that everything that they do in BCI.
You don't have to do any, I didn't make any unique construction at all. I just plugged Z into their thing. I did some work to prove that it works. But
Yeah.
it's there, it's McDuff's.
There are McDuff examples where the group is Z.
Constructed, the way Lunene and Jonas Adrian presented, they're always working with this ICC non-amenable, right, group.
Mhm.
But that's because in their head they're going to plug in they're going to plug in F2, but there is a lot that just works with any group, and so you just plug in Z and just check that the right things work.
Oh, very nice.
Okay.
It's the same thing when you work with Sakai's construction. Sakai had independently.
Oh, yeah.
Yeah, but like, okay.
Okay, we've
so
got continuum many, and there can't be more than continuum many, so, okay.
I had a question.
Oh, hold it, that wasn't your question?
No, that was not
You
my
made a question, we got an answer for it.
Yeah, that's nice.
Okay, you were responsible for wrestling the microphone out of people's hands, too. Okay, you can recruit others. Okay, go.
So let me ask my question. Is the existence of an index 2 subfactor in the theory of, in 2-1 factors, is that an elementary property?
The existence of an index 2. Subfactor of a 2-1 factor, right?
To the next person, I just have to say for potential employers that Stephen is a very nice and modest person. It is not that simple. So, any Elon for the question?
Sorry, that's something I asked him. If we're talking about the choice, then the question was: is any Hilbert space, is any complex Hilbert space complexification of a real one?
Sorry?
Is any complex Hilbert space without choice a complexification of a real Hilbert space?
Is any
Okay. Yeah. But if
any C Hilbert space? The complexification of a real Hilbert space. It's just assuming ZF. Is that
Okay, any other question, Chris?
Okay, so this is essentially the same question as before, but about a different collection of things, namely Higgs P between 0 and infinity, and look at the class of LP operator algebras, which are closed subalgebras, boundary operators in the same LP space. So in this case, it actually is obviously closed under ultra roots. The subalgebras are against such things. But is it effectively axiomatizable? Can one find some usable collection of axioms?
So is the class of, so what are we
LP operator algebras.
operating?
So first question was the case with using equal to.
Right.
No, it wasn't, because that was C star, not.
Okay, so is the
No.
class of LP operators or operator algebras effectively axiomatizable? And you say it's obvious. Sorry.
In Banach algebras.
It has right.
Yeah, so it's known this is close under ultra powers.
As
The ultra root part
As
is obvious because subalgebras of LP operator algebras are LP operator algebras.
right. So it is axiomatizable.
Yes.
Or it's elementary, and then the question is whether there's a set of effective. This feels like the question that you should ask Ward Henson. You know that.
And so the third one I want to know is for now some class which contains all, again, among Banach algebras, which contains all C star algebras.
Is there or given a class?
No, is there a class?
Is there an elementary class
An axiomatizable class
containing
all C star algebras and the algebra of just n by n matrices acting on little LP of n points?
and sorry?
And n by n matrices normed as acting on little LP of n points for all P.
LP,
Little LP, yeah.
little LP n,
N points,
right?
yeah.
For all n.
So an axiomatizable class which contains those things and contains no Hilbert space operator algebra that's not a C star algebra.
And doesn't contain a Hilbert space
Operator algebra, which is not a C star algebra.
okay.
Yeah, so that should be LP of n for all n and for all P.
Right, and
Or P, yeah.
yep. So just as a comment, you can always do this. This is a standard trick like I did up there. You just take all those things, take the elementary class you get from them, and so your question is whether or not these guys necessarily satisfy the theory of those guys, right? So if you could come up with sets, a set of axioms for the, things that hold in all of these, then the question is whether or not they necessarily hold for these.
Yeah, and again, I want effective and real.
Right,
So
yeah.
axioms and so on. But if it doesn't exist at all, then yeah, be effective. So.
Right. If yes, is it effective? And what do you want this for?
I want to know what a C star like LP operator algebra should be.
Okay.
I had a conjecture which turns out to be false. A refined conjecture was also turns out to be false.
And this is what you're left with.
One was no, an actual specific axiom.
Oh, I see. A specific axiomatization.
I'm not sure if it would be axiomatizable in the sense of model theory or whatever, but hope for characterization. The original version turned out to be easily shown to be false. The refined version is still false, but the example was not easy to find.
Okay. Okay.
Okay, any other questions? I actually have another one, which is more model theoretic, also about phenomenal algebras.
Okay.
So first, there is saying the same, and I have a theorem recently that if you have measurable field of 2 1-factors, let's say mt, for t in 0, 1, that you can compute theory of the direct integral of mt's from theories of mt's.
Do you want me to write this? Like, so given, okay, given a field of 2 1-factors,
2 1-factors, yes.
factors, m sub t,
0, 1, or some measure.
right, t in 0, 1,
So it's a measurable field. So it's
right,
like
so,
you have you can make sense out of direct integral.
mhm.
And then you can compute theory of the direct integral
Then,
of mt's.
right, then the integral mt d mu, the theory of this can be computed from theory of mt for all t.
So question is basically, is the converse true? If you know the theory of direct integral, can you from there compute what is distribution of theories of this?
So is the converse true?
Of course, you have to be careful. Exactly.
True.
So we actually stated it slightly different. I just wanted to oversimplify it.
To,
So basically, the proper way to state the converse is to fix any sentence and to just look at the evaluation of that sentence in MTs, and that gives you some random variable. And question is, can you compute all those random variables for each sentence from the theory?
so you're actually guessing at how you evaluate a sentence in the direct integral from.
Well, we know how to evaluate sentence, but question is
Oh.
converse. Can you, if you know evaluation of all sentences,
Okay.
So can you figure out the distribution
know
of all the
theory of the integral.
So I hope it's clear. So if you fix any sentence phi,
Right.
there is a function which sends phi
Then
to a value of phi in mt, then that's a random variable. So are those random variables uniquely determined by the theory of vector? So if the answer is positive, then the question, so I'm going to split that question, do tensor products of two 1-factors preserve elementary equivalence? If the answer to this is positive, then the answer to the first one is if and only if tensor products of two 1-factors preserve elementary equivalence. Because say then I worked everything else.
okay, so because I was writing, I missed your question.
So question is, if M are rotational fundamental algebras.
Whoops, I should probably do this.
And M is elementality over 20. So and there is one.
Just two, okay.
So that's it.
Okay.
And P is another rotational fundamental algebra. Is M tensor P elemental equivalent to M tensor?
Okay, so these guys are all tracial DNA. Then is M tensor P elementarily equivalent to N tensor P.
So a positive answer to the previous question would reduce these two questions about 1-factors.
Okay. And the answer to this question is, of course, no, but so conditions on such.
We don't know any countries.
I know, but it's still no.
In C-star case, yes, but dissertation is no.
It's false. It's false. Yeah, it's false in C-star algebras.
Even if you tensor with Z, even if you tensor continuous functions with 0, 1, I mean, for P, so you can.
It's very. in the C
We don't know, that's all.
in the C-star algebra
We have
case,
seen this
right?
in
Yeah.
local values.
Any other questions?
Lunch.
Last question, what's
Oh,
lunch?
what's for lunch? There you go. Excellent.